Hey there, in this video I'm going to talk about numerical differentiation. And if you think back to the beginning of calculus class, way back maybe even in high school, the way you learn calculus is by first learning about limits, and you're introduced to the derivative through doing a limit. We're going to go all the way back to that, and that's the definition we're going to use for our numerical derivative. So df dx is going to be equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. In other words, we take our function at location x, take a small step h forward, subtract those two, divide by h. That's then the slope, or at least an approximation of the slope or the derivative. This approach is called the forward difference because we're looking forward. Just the fact that it has a name sort of implies that there must be a backward difference, and sure enough there is. We don't have to take a step forward, but we could take a step back and calculate the slope that way. And in the limit h actually going to 0, these would be identical. In reality, we're going to use values of h that are just tiny, so they won't numerically give you exactly the same value, although hopefully they're very close. So we'll do x minus h here for the second point. And if you're wondering, well, why do we need both definitions? Suppose we have an array of data and we're trying to calculate the derivative throughout that array. So we've got points that are like something like this. We could only do a forward difference for the first point because there is no point before it to look at, and we could only do a backwards difference for the last point. And for the middle point, we could go forwards or backwards. Or we could even do some kind of average of forwards and backwards, which is actually the best approach, doing this average called a central difference. Before we go into the central difference, let's talk about the accuracy of the forward difference, and it's going to be identical for the backward difference. To calculate the accuracy, what we're going to do here is do a Taylor expansion and look at whatever extra terms are there that didn't show up in our simple equation. We're doing the Taylor expansion of f of x plus h, like that term that appears in the forward difference, and we're going to do the expansion about the point x. So f of x plus h is equal to f of x plus h minus the expansion point, so minus x, f prime of x plus 1/2 x plus h minus x squared times second derivative of x, and then so on. But that's enough terms for us to estimate our error. And this simplifies a bit because we have x minus x canceling out. So this is going to be f of x plus h f prime of x plus 1/2 h squared if f double prime of x, and so on. And what I want to do here is I want to solve for the first derivative. So as long as we keep all infinity terms, no big deal there, then this would be an exact solution for the first derivative. We won't keep all infinity terms, but what we're going to see, keeping just a few terms, is that rearranging, I'm trying to solve for the term that's over here, I'm going to get f plus x plus h, that's my original left-hand side from over there. I'm going to subtract f at x, divide those by h. Really, I'm going to divide every term by h, but we'll put those in this form because, hey, that looks a lot like the forward difference rule, just without the limit part. And then what are the other terms? Well, we're going to have an h squared on 2 divided by h, so that's going to be a total of h on 2 times the second derivative of x plus everything else. And so that's my error, and the error is going to scale like h. Okay, so now let's look at what is the ideal h to use. Now, if you were right now screaming at your computer 0, no, it's not. Not in a computer, it isn't. If we actually put in 0, we'd get a division by 0 error. Okay, well, how about something really tiny? Yeah, but how tiny? You see, there's actually two issues here if we're talking about a computer. So small is good, right? Because the error here scales like h. Well, that's actually only part of the error. This first term over here, that also has some error. And that has to do with how accurate your computer is at subtracting two values, two nearby values. So f at x plus h and f at x are two numbers, two floating point numbers that are really, really close to each other. And that can be terrible in your computer because your floating point numbers only have a certain amount of accuracy, or a certain amount of precision, a certain number of decimal places. And if they are closer than that, when you subtract them, the computer will say 0. And that's not really what you want. Otherwise, your derivatives would always be 0. And so the error you get here depends on the computer's precision. So I'll do C here for computer's precision. And then we have a divide by h that's explicitly in the equation. So it's like a ratio of the computer's precision on the step size h. So the second issue here is rounding error. So rounding error is bad if h is too small. So the total overall error is going to take the form C on h plus h. We want to add up those two terms. So the leftover from the Taylor expansion is the h, the rounding is C on h. Okay, so if I minimize that, minimize in a calculus sort of sense, so I take the derivative with respect to h, set that equal to 0. That's really not all that hard with the equation we have here. We get that h should be about the square root of c. And that would then lead to an error that's like square root of c also. And so with c being about 10 to the negative 16 for most computers, this depends on operating system and Python version, but I'd bet money that it's 10 to the minus 16 for you. We plug that in, we're going to get that the ideal h here is not just some small number, but specifically it's about 10 to the minus 8. And that would then give us errors. We do that of 10 to the minus 8. Okay, now before we run off with that result, we do have an improvement we can make. I mentioned before when we were talking about these points here, how a point in the middle, you have the choice of stepping forward or stepping back, and why not average? And that's, in effect, your best way to do this. Let's look at the central difference. So the central difference, df dx, is equal to the limit as h approaches 0 of f at x, take half a step forward, minus taking half a step back. Divide all that by h. And that's our most accurate way to do a numerical derivative. The reason it's more accurate is if we go and do the Taylor expansion for this, following the same steps as on the previous slide, we find that there's an extra term that cancels out. The second derivative term will also cancel out, and the next term that survives in the Taylor expansion is the third term, as the third derivative term. And so we end up with h scaling like your computer's precision to the 1/3, giving you an error that scales like c to the 2/3. And so using the central difference, our ideal value of h is 10 to the minus 5, giving us then an error that scales like 10 to the minus 10. And so that's a factor of 100 improvement in the error, and we get to do bigger step sizes, which means more computation. And it's a very little change. This is really cheap for your computer to calculate. So your ideal, where you have an array with a bunch of values, is to do a forward difference for the first point, a backwards difference for the back point. That's your only choice because there's nothing on the other side of those. And then you do central differences for all the in-between points. Let's look at how we can calculate a derivative with NumPy. So NumPy has a built-in for us called gradient. And gradient here takes f, which is an array. It can be a more than one-dimensional array. So I'll show you a 1D and a 2D example. And a little unclear here when it says like VRARGs, that's hard to say, VRARGs, those are the spacings. So let's create some data first. Let's say our x values are a range 0 to 100 in steps of 10. And then I want to make some y values here. We'll do something simple like x squared. Okay, now if I want to calculate the derivative of y with respect to x for this array, so it's going to give me an array of derivatives. I'm going to call gradient, and I'm going to give it y. One of those important varargs that we need in here is the spacing. And if we look, in our case, my spacing was 10, so I want to make sure I put in 10. I could also put in the entire value x. So let's just check that that works for us. So we'll do dy dx here printed. Okay, so the derivative here, 10, 20, 40, blah, 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 all the way along. What if I put in x instead? Same thing. What if I don't put in anything? Okay, look at that. It got the spacing wrong because it's going to make some kind of guess, which I think it defaults to guessing 1, which gives you a very different slope in that case, off by a factor of 10, as it so happens. So you want to put in the spacing here as that second argument, or put in the array of x values if you have access to that. Now let's try a quick plot here just to make sure visually we can see what's going on here. So I'm going to do a plot of x dy dx, and we'll make those dots. Okay, so that's what I'm calculating with gradient, and I want to compare it to the analytical answer. I mean, we can do this derivative in our head, right? And we're going to get 2x. So let's plot x versus 2 times x, and we'll make that one a solid line. Solid line is the default, but I'm typing out here just to be really explicit about what I intend the code to do. Never hurts to be explicit. And we're going to do plot.show. Okay, so the dots are what was calculated. The line here is the actual. You'll notice the endpoints aren't great. They're a little bit off. What's going on here is for the endpoints, it's impossible to do a central difference. So the first endpoint uses a forward difference, the last endpoint uses a backwards difference, and those are just not as accurate as a central difference, which is what all the other points are. That's why they are more accurate. In this case, it's especially visible because it's a straight line, but for any kind of function, the middle points will be more accurate than the endpoints with gradient. Let's look at a two-dimensional example. So we're going to make f here. Yeah, f's fine. And let's make it a 2D array. So we're going to make it as a list of lists. Let's go with like a 3x3. Get that lined up nicely. All right. And we're going to put in 1, 2, 4, 1, 2, 4, 1, 2, 4. So if we think about the gradient here, like this two-dimensional slope, I've got a step of 1, a step of 2 as I move left to right, and I have steps of 0 as I move vertically because they're all identical. And I chose those values just so it should be really clear which one was the x answers and which ones were the y answers. Let's look at when we run gradient, what comes out. So np.gradient f, and it's a good idea to have some kind of spacing explicitly in here just so you don't forget to do it, even if the default I think is 1. We'll just explicitly put the 1 in there. Okay, and so what comes out? What comes out is a tuple of values, which if you think about mathematically how the gradient works, the gradient is supposed to give you x components and y components, so yeah, you're going to get 2 values. The first one that came out was all zeros, the second one that came out was 1, 1.5, 2. Where those numbers come from. Well, as I move left to right, that's clearly a step of 1, that's doing a forward difference, like a really easy forward difference. 2 minus 1 divided by 1. This step here is a backwards difference, that's 2. And what was in the middle, that was a central difference, which is like averaging 1 and 2. That's how we get 1.5. Now the thing is, the first thing that popped out, that's not the left to right. That is not x. Y comes out first and then x. What's going on here is these are arrays, and arrays are ordered row column. So if I wanted to put these into variables with tuple unpacking, it kind of looks backwards. I want to do df dy first and then df dx. It's a super common mistake using gradient is to switch your x's and your y's. They come out what looks like backwards because they're ordered row column, not xy. Okay, so watch out for that. Guarantee someone's going to make that mistake.